Section 4.1 Maximum and minimum values, as you can see from the title. So what is this section about? If we are given a function f of x or some random graph, the question is, how do we find the min and maximum values for either the function or the graph of any given function? So how to find that out? Before we learn how to find the minimum and maximum values, it's important to kind of classify them. So for maximum, we're gonna write max, minimum, min values. There are two different kinds of min and maximum. One is called absolute, and some people call it global. We're gonna be using absolute just in case if you come across it, another name for it is global. So absolute min or max, and then we have local, or some people call it relative. Two different kinds of min and max we're gonna see. Now those minimum and maximum, so to find the minimum and maximum values, if it's absolute or local, we are actually finding the y values. But to do so, we need their x values. So we need their x values. And that's what we're going to learn today, how you find those x values. That would give us the maximum or minimum values for a given function or graph. The first thing is kind of learn more about this, the language of minimum and maximum. So the maximum and minimum values of, let's say, a function f are called extrema, or extreme values of f. So sometimes instead of asking you to find min or max, they ask you to find the extreme values of f. That means the same thing. Note the extreme value or extremum, which is a singular of extrema. So extreme value, some people say, or extremum, just in case if you are asked to find the extremum or the extreme value, they mean the same thing. We start with the local first. Introduce what local means, why do we call it local or relative. So the local, start with the local. Local min or max of f, of function f, over is the minimum or the maximum value that the graph or the function can reach over a specific interval. So basically it's within a neighborhood. It's within a neighborhood. So it is over a certain neighborhood. That's what local. Local means locally, it's just locally within that neighborhood. What's the maximum value or the minimum value the graph can reach? Within that neighborhood, is there a min and or maximum value? Let's look at a random graph like this. This is a graph of f. Well, this is within this neighborhood, like somewhere here. That's the local minimum. This is local maximum. This is local minimum. Notice the graph can have more than one local min and more than one local max, or only local min or only local max. So how can that happen? Well, if you have this, there's only local min, no local max. What about if you have something like this? That's a local max, no local min. Here oh sorry, this is local min, no local max. So it can have 2, 3, 4 if each one of them, or just one of them, or one of, either local min or local max. So that's what local. And now when we finish the next point, then you get the big picture of how you differentiate between all of this and how we find them out. So now I'm going to do the intro about the absolute. So the absolute min or max occurs or can be found over the entire domain of a function or a graph. Graph means a given graph. So this will tell me the maximum point the graph can reach. Where is or are the x values where the graph reaches highest point over the entire domain. Note, it can be at the endpoints. Point or points. And I'll show you that on the graph what that means. Let's say I'm gonna look at something like this. So the graph started, see, I didn't put arrows on both sides. In the earlier graphs I put arrows. That means the graph goes forever. If you see the arrows, it goes forever. But this one, it stops somewhere at that point. Let's call that point A. I'm gonna call this point B. I'm gonna call this point C. I'm gonna call this point D. So if we look at the entire domain from point A to point D, like all the way, the maximum point the graph can reach is at point A. So at point A, there is an absolute max. Where is the point where it reaches the lowest over the entire domain? It's at point B. That's the absolute min. But students might say, wait, what about point B again? Can I just call that also local min? The answer is yes. Within that neighborhood of point B, that's also called local min. So you can have a point that can be called both at the same time, local min and absolute min. What about at point C? Well, that's a local max. What about D? Nothing. Notice something. When we talk about absolute max and min, it can occur at the endpoints, and that's what happened to the absolute max for this graph. It occurred at the endpoint, at point A. So the points inside between A and D, those are the only ones that can be local min, local max. And that's why in the previous examples here, I didn't care about these arrows on both ends. I just looked inside, within a certain neighborhood, so it's not the endpoint. So the local min and max, they can only occur inside the interval, like not outside. So over the interval, the open interval AB. But here it can occur over the closed interval AB for the absolute ones. What about an example like this? What is this? What's the absolute min, absolute max? For such a graph, there's no absolute min or max. No local min or max. That's what this graph is about. No local min or max. So what about if we look at another example, a different example? X, Y. Say this goes this way. And let's label them. Let's call this. This is 5, 4. Point A. This point here, 3, -4. Point B. This point, let's call it 1, 2, C. -2, -1, D. This point, -3, 2. About 2. E. So let's see what each point, what can we say about each point. The first thing, that it's a closed interval from -3, like if you drop it down, that's a -3, all the way to 5. This point here is 5. So this function, the domain of this function from exactly -3 to exactly 5. First thing, the highest point I see is point A. So at point A, there's a local max. Sorry, absolute max. Absolute max. And at B, there's an absolute min. Again, at B, we can say there's a local min. At C, there's a local max. At D, there's a local min. That's it. E, nothing. It's not local. It can be at the endpoint, and it's not the highest or lowest point the graph can reach over its domain. So we can simply ignore it. Now we introduce a theorem, actually two theorems. The first one, the extreme value theorem. What does it say? It says if a function f is continuous on a closed interval AB, then f attains absolute maximum, absolute max value, f of c, and an absolute min value, call it f of d, in the interval, the closed interval AB. So it can be at the end point. That's what the closed interval means. So two conditions should be met: continuity, and it has to be a closed interval. If that happens, then that forces the function to really attain an absolute max and one absolute min. So this means the graph must reach a highest point somewhere from A to B and a lowest point somewhere from B to A, or A to B. So there has to be, or must be, one max and one absolute min. So let's look at small sketches here. Let's say something like this. Does that satisfy the conditions of the extreme value theorem? Yes, this is okay. It's a continuous function, okay, and the interval is a closed interval. So this is fine. What about another example? Let's say it goes this way. Is this continuous and closed interval? Yes, it is. What about if it goes this way, up and down, like all the way here? Is that continuous? Yes. It's a closed interval? Yes. So the third one, this one is okay, this one is okay, it satisfies, and it must reach a maximum value. Like for the first one, that would be the absolute max. So this would be the absolute max. This would be the absolute min. It must. This here, the absolute min. This is the absolute max. The other one, the same thing. Now, what about if we have a different graph? Let's say we have a graph that goes this way. There's an open thing here, open circle, and this goes down. Let's say this point is 3, x, 0, y. Notice this has absolute min at x equals 3. Where's the absolute max? We don't know. Well, what happened to the extreme value theorem? Well, it fails. So this thing, it fails. The extreme value theorem why? Because it is not continuous. It's not continuous. What about another example? I'm gonna draw a line here. That's what we call a vertical asymptote. And then let's say it goes this way. So if we look at this one, what does that satisfy the conditions of the extreme value theorem? Continuous, it's okay. But wait, it's not a closed interval. It's not a closed interval. So the absolute min and max, both of them do not have to be attained. So that's why we ignore that. Means I do not have to worry about the finding the absolute min and max for this specific function. I'm going to introduce another theorem. It's called Foremast theorem. Foremast theorem. Fermat proved several theorems. One of them is this one that says if a function f has a local min or max at, let's say, x equals c, then the derivative at c is 0 or the derivative at c does not exist. So I'm going to write D and E means does not exist. It's an abbreviation for does not exist. So this is very important thing here for this whole chapter. If f has a local min or max at a point c, then this means the slope of the tangent line, this is the slope tangent line, is 0 or the slope does not exist. So what does it mean 0? 0 means something like this. It's a horizontal tangent. Right? That's what the slope of the tangent line is 0. So any horizontal line has a 0 slope. This one is again the slope of the tangent line does not exist. Does not exist, this means there's a vertical tangent. Let's say like this, you have a vertical tangent. That's not exactly a function, but you have a vertical tangent. Or there's like maybe a cusp or something like that. Something like this. That's a vertical tangent, like that. So that's what does not exist means. So again, you need to know that f prime at c, that represents the slope of the tangent line of the function f at x equals c. So if there's a local min or max, one of these two conditions must occur. For example, let's say we have a graph. If the graph of f looks like this, well, at this point, I see the graph has a horizontal tangent. So let's call it A. Again, there's one here. Let's call it B. So we say both f prime at A is 0 and f prime at B is 0. The slope of the tangent line. That's what it means, f prime. So there's a local min. So note at x equals A, f has a local max. At x equals B, f has a local min. That's what this means. So now, what about I'll show an example later on about this. For the meantime, let's say the f prime at c equals 0, or the ones that we wrote earlier, does not exist, provides all possibilities. all possibilities where f might have local extreme values. So these will help us to locate the minimum and maximum. Okay, so I wanted to show another example on top of the ones that I showed earlier. So let's say we have something like this. So at this number, let's call it x1, and then there's another number. These two are 2x values important. So what do you see here? At x1, there's a horizontal tangent. Call this f. So f prime at x1 is 0. What about at x2? There's no horizontal tangent, there's maybe vertical tangent, or we call it cusp there. So f prime at x2 does not exist. Does not exist. These two numbers are called in the calculus language. Note that x1 and x2 are called critical numbers. x1, x2 are called critical numbers. So what is a critical number? Well, we can define it, introduce definition. We say a critical number of a function f is a number C in the domain of f, domain of f, for which f prime of c is 0 or f prime of c does not exist. So any number within the domain of f that gives you the slope of the tangent line at that point is either 0 or does not exist, means that number c is called a critical number. It's called a critical number. Let's say they didn't give us a graph, but they give us an actual function and they ask us find any critical numbers. Any critical numbers. Let's take the first example. Y equals f of x, x cubed minus 6x squared plus 9x plus 2. This is a polynomial function. You know, the domain of this is all real numbers. So how are we going to find the critical numbers? Well, notice how the derivative must be 0 or does not exist. So the first thing that motivates us to do here is to find the derivative of this function, which is 3x squared minus 12x plus 9. So is there a way that this would make it does not exist? No, usually that happens with fractional function, like rational functions. But can that be 0? Well, let's try. I see I can divide everything by 3. That makes it simpler to work with. We are hoping this is factorable, is it? X minus 3, x minus 1? Yes, it is. So then what we get x equals 3 and x equals 1. So the critical numbers are 1 and 3. What about y equals f of x 1 over x minus 2? So what do we do here? Always we find the derivative first. We start finding derivative. To find the derivative of this, what do we use? We use quotient rule. Quotient rule says you square the denominator times the derivative of the top minus derivative of the bottom times the top one. So let's see what we get here. Derivative of 1 is 0. So x minus 2 times 0. Derivative of x minus 2 is 1 minus 0. So 1 times 1, and keep this the same. Then f prime of x equals 0 minus 1 is negative 1 over x minus 2 squared. So we are going to see when does this equal to 0, or what is and are the values of x that would make this 0 or does not exist. Or does not exist. So can this equal to 0? Well, if it is equal to 0 and you cross multiply, you're going to get negative 1 equals 0. Boom, doesn't work. It can be 0. When is f prime does not exist? So f prime of x does not exist when the denominator is 0. That means when x is 2. So now we say x equals to a critical number, right? The answer is no. And you might say, wait. You said critical numbers, you find them by either setting the f prime of x equals 0 or does not exist. And what's wrong about x equals 2 here? Well, let's go back to the definition. So it says a critical number of a function f is a number c in the domain. It must be in the domain of f. Well, let's go down back to this one. What's the domain for this function? Well, domain of this is it's all real numbers except what makes the denominator 0, except 2. So 2 is not in the domain. 2 is not in the domain. So this one, so x equals 2 is not in the domain. It's not in the domain of f. So x equals 2 is not a critical number. It's not a critical number. So what happened to this function? This function has no critical numbers. This function has no critical numbers. Let's look at more challenging one. Say x minus 2 to the 2/3, all that divided by x. So what do we need to do? We need to find the derivative of this. Okay, so there are two ways to find the derivative. Either you can use quotient rule, or you can bring the x up and use product rule. Okay, either one would be fine. So let's use quotient rule. Quotient rule again says this times the derivative of the other one minus the derivative of the denominator times the second one over the denominator square. X stays the same. What is this? You bring the 2/3 down, x minus 2, and subtract 1 from that. 2/3 minus 1, it's negative 1/3. Derivative of x is 1, and this stays the same over x squared. So what confused students the most is working with something like this. How am I going to solve this equals 0 or does not exist? First thing is we use the exponent properties. So the 2x stays up there, and I bring that down, x minus 2 to the 1/3. So no negative exponents. This has no negative exponents. I keep it as is, and this stays the same. Notice this is over 1, this is over 1. The easiest way to simplify such fractions, which we call them complex fractions, is to multiply by the least common denominator, which is 3 times. So we multiply here by 3 times x minus 2 to the 1/3. We do the same thing, 3 times x minus 2 to the 1/3. 3 times x minus 2 to the 1/3. So the derivative here is, these cancel out. I get 2x minus 3. When I multiply these together, they have the same base. I add the exponents, the 2/3 and 1/3. 2/3 plus 1/3 is 1. So that gives me just x minus 2 to the first power. Denominator stays the same. Now what are we left with on the top? keep this the same. In the numerator, we got negative x plus 6. Negative x plus 6. So now, how do we finish that up? How do we finish that up? Well, I simplified everything in the derivative. We got the derivative. We're halfway through. Now we're going to see when is the derivative equal to 0 and when is the derivative does not exist. Well, this equal to 0 when the numerator is 0. So when negative x plus 6 is 0 and x is 6. So that's one of the values we got. When is this does not exist? When the denominator is equal to 0. And this can equal 0 when x squared is 0 or x minus 2 is 0. So that means when x is 0 and x equals 2. I'm going to box both for now. But I need to make sure to go back and check the domain of the function. So this means I'm not including something. What's the domain of this function? Domain is all real numbers except 0. So 0 is one of the values? Oh yeah, so we cross it out. So this function, the function has two critical numbers. Six and 2. 6 and 2. So this, what we have been doing in all this just to find the critical numbers. Now, why do we need to find the critical numbers? Because the critical numbers will help me find the local min, local max. And it will help me to find absolute min, absolute max. So from these numbers, I can easily substitute them back in, which I'll show later on how to do that. And then to get the corresponding y values. But for the other part is the pupil asks a question, how do we locate the absolute min and absolute max if we have been focusing on local min and local max? So the question is how to locate the extreme values. So in other words, how you find the absolute min and absolute max. So absolute min, max. How do we find them? Okay, so to do so, there's some guidelines. So let f, a function f, be continuous over the interval AB. Then the absolute min and max values of f are the smallest and largest, as we defined them before, values respectively, found, those can be found using the guidelines. The first guideline, by finding the values of f first, values of f at the critical numbers. At the critical numbers in the open interval AB. So whatever critical numbers you found, as we did in the previous examples, you just find f of those numbers. And also, we find f of A and f of B. So basically the y values at the endpoints. Whichever maximum value we get, let's say f of b is the largest, that would be the absolute max. And then maybe x1 is a critical number and f of x1 is the lowest. That would be the absolute min. So let's look at an example. So we need to find the absolute min / max values of each function. And what I'm going to do is I'm going to take the first example I presented today, which was x cubed minus 6x squared plus 9x plus 2, but they added some condition here over 0 comma 2. Otherwise I can't find absolute min and max, maybe. Right? For sure we can't. It has to be a closed interval. So remember, we found the derivative earlier. If you look at the derivative, let me go quick over this. 12x plus 9. We set it equals 0 and we solved for x's. One of them 1 and one of them was 3. Now these are the critical numbers. These are the critical numbers. We are going to evaluate this function at the critical numbers, f of 1 and f of 3, and also going to evaluate it at the endpoints, 0 and 1 and 2. So f of 0 and f of 2. Now one thing before I forget, it's important that make sure these critical numbers, they are within that given interval they give you. So 0 to 2, are these two within that number? Well, 1 is there, but 3 is not. 3 is not within that interval. So what do we do with f of 3? We don't have to worry about it. So that saves us some work. So f of 1, just substitute 1 into the function. So which is not difficult to do. So it's just 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. That will give us 6. F of 0 is the easiest, is 2. And f of 2 is 4. So notice which one is the highest value, this one. Lowest is this one. So this means there's an absolute max at the point 1 comma 6. And there's an absolute min at the point 0 comma 2. The value of that is 6 and 2. That's the highest the graph can reach. How about we look at another example from the one that we did earlier. Y equals f of x. It was x minus 2 to the 2/3 divided by x. And I'm going to add an interval to this. Let's say 1 to 10. 1 to 10. Well, if you remember from previous example, we found the derivative of the function. It was 6, or no, it was negative x plus 6 over 3x squared times x minus 2 to the 1/3. And we found that x equals 6 and x equals, what was the other one? There was x equals 6 and x equals 2. These two values are critical numbers. These two were critical numbers. So now what we need to do is to evaluate the function at 6, at 2, and at the endpoints 1 and 10. 1 and 10. Wait, let's check the critical numbers. 2 and 6, are they within 1 to 10? Yes. So this means we must substitute those, all of them, into the original function, not the derivative, because you're finding f of 6. So that would be like 6 minus 2 to the 2/3 divided by 6. And if you put that in the calculator, that would give about 0.42. F of 2 the same way, and I got 0. F of 1, I got 1. F of 10, I got about 0.4. So which value is the highest? This is the highest value. So there's an absolute max at this point, and there's an absolute min at this point. That's what this section is about. It's about how to find minimum, maximum, and there are two different kinds of min and max. One called local or relative, and the other one is absolute or global. And so we looked at the difference between both of them, and at the same time, we learned how to find them. We introduced what we call critical numbers, okay? And then we looked at an example, both graphically and algebraically, how we find them using calculus. And out of this, the question would be, why do I need to learn this? And to answer this question, we're going to see it in the subsequent sections as we go through this chapter. But that's the beginning of chapter 4, and that's what we are learning now. We're learning new terms, new vocabs. That is the language of this chapter. And then we're going to apply all of this in the subsequent sections. And that's what really this section is about.